Thanks, Kate. And thanks to all the other staff. This event's great. It's my first time here. I've really enjoyed the whole thing. Feel really honored to be part of this, so it's great. I'll just jump right in here. Just finished my slides like 10 minutes ago in the next room. Don't ever do that. Finish early. So you guys get an unrehearsed slide deck. Should be great. So here's the agenda, and I think I stuck to that. So a little about me. My handle is jduck. I did a bunch of exploit dev at Metasploit for a couple of years, or a year and a half. I've been researching stuff for many years. Linux since, back when nobody knew what the hell Linux was, and been doing Android for about a year and a half now. So we're working on a book, actually, the Android Hacker's Handbook. It's available for pre-order, but it's not done yet, so you'll have to wait till we finish it. So why look at the background? Why look at the proprietary stuff in Android? So it turns out that Android was proclaimed by one of these magazines, and I can't remember off the top of my head which one, but they said that actually Android is the most popular operating system on the planet, not just mobile operating system, but actually like the number of Android devices actually outpaces like all other operating system portions of all devices. So I thought that was pretty interesting. Android has a really complex ecosystem, and I'll show you some more about that in a second. Mostly ARM. It's Linux based. I don't know if you guys are all familiar with Android at this point, right? I could probably just skip this whole thing. This little slide. So let's go to the next one then. So this is sort of a awesome diagram that's really crazy because it kind of indicates exactly how crazy this ecosystem is. Each one of these arrows kind of is a relationship that has to do with what they have to do, like back and forth communications to deal with certain parts of Android. So it's kind of a mess. And on the right-hand side, you'll see the areas of the system that each of these groups of people like mess with. And you can see, like with Google and OEMs both changing everything and making a giant mess, then it gets really ugly. And yeah. So ARM. It's mostly ARM devices, but the thing about Android devices is that like there's really no two that are alike. They're kind of like snowflakes in that regard. So I've been collecting them. So I have this is an older picture, but I think this shows 26 devices. Right now I have 34 devices. And so like in order to really get an accurate picture of any particular device, you actually have to have that device. It's kind of unfortunate, but it makes for cool pictures with massive USB hubs. So again, back to the proprietary stuff. I think the guy JBQ, and I wouldn't pronounce his name because like I'll just get ostracized by everybody here for getting it wrong. But anyway, this guy is the guy who actually pushes all the open source stuff for Android. So when Android makes a release, like it's his job to wade through the mess of commits that they've made in the last, I think since the last release, it's been almost 6 months. So I think he's got his work cut out for him pretty soon here. But he said this outside of proprietary device-specific files, so he's already hinting to something. And then he says everything's open source except for the Google-specific code. So I thought that summed it up really well, because it pretty much does fall into these two groups. If you've ever tried to build an image for a firmware for an Android device from AOSP, like a Nexus device, then you'll find that you actually have to go download these binary drivers and stick them in just some magical directory in the build tree, and then they get slipstreamed in there during the build. So there's been weird things in the past where, like the Nexus 4, they released Jelly Bean 4.2 with it or something like that, and then they released the binary images, and suddenly, like the factory images and the binary images, they all disappeared one day, like the second day that they were up there. So that was kind of fun. Nobody knows why they won't ever talk about why that things happen, but. So sometimes the things are differ. Like I noticed with the Nexus 4, like the live device has modules disabled, which I guess is a smart thing for security. But the kernel source itself, like the thing that they ship to everybody that you're supposed to use to build a kernel, doesn't have that configuration. So it's kind of strange. Not really in line with open source. So let's get into a little bit more about the proprietary code and kind of what there is in there. When you look around an Android device, you think that everything's going to have source to it or whatever, but really, you'll find stuff all over the place, and it really varies from every device to device. So you could end up with stuff that's kernel modules that are custom. You could end up with completely new implementations of entire protocols implemented in userland. You can end up with lots of stuff in the lower level areas where the bootloaders are all closed, and everything sort of below Linux kernel is really all pretty much closed source. So even in apps, you download an app off the Play Store and you play it and you look at it, and it's actually got like a 12 meg ARM binary library inside of it, and that's how you're actually playing. So it gets kind of really messy in that area even. So further, what kind of stuff is under the hood before the Linux kernel? The whole boot chain is like 6 steps long or something on Android, and so the bootloaders and the trust zone. When I say bootloaders, it's because there are so many stages, and then trust zone actually gets booted during the process before anything else happens. So and the baseband as well. So these things are all proprietary, and in fact, you can't get any information about baseband or trust zone really. Some of the bootloaders are based on open source, but most of them are completely proprietary as well. Kernel space drivers. Sometimes you find drivers for different things, and there's something I'll show later, but it's based on some third-party driver that's in this tablet. We'll talk about it more later. But also the Broadcom drivers that were mentioned a couple talks ago. The firmware for those are on all these devices. In user space, the RIL daemon, it stands for Radio Interface Layer. That daemon is actually completely open source, but all it really does is loads a shared library that's completely proprietary. So it's really interesting, and that one is less specific to each device and more specific to kind of the actual OEM or the network which it's compatible with. So it's kind of interesting in a little subzone. The other thing about RIL is it's kind of like a remote attack surface, because everything goes through there that comes through the cellular network. So that's fun. So also in trust zone doesn't have any persistent storage other than a very small amount of space in the internal RAM. So with trust zone, they use actually a user space daemon that sits there and talks to a kernel module, which then talks to trust zone, and it keeps asking hey, do you guys have anything for me to do? And then trust zone will actually give it encrypted file system contents to just store locally. So they've got this whole chain, and it's kind of retarded, but I understand secure RAM is expensive. So about the device tree concept, I looked this term up because I wasn't sure entirely about this, but I had seen a lot of people talking about it in ROM development and on XDA forums and stuff like that. And the formal definition was something that I was so confused with. Apparently, it's way deeper than what I thought it was. But the way I see people use it, I don't think that they're talking about the same thing either. So in AOSP, actually, there's a device directory. If you ever checked out ASP before, the device directory, you don't usually get it by default, so you kind of have to check things out that are in there directly. But that includes makefiles and other things to help you build the binary blobs, although it doesn't actually include, I don't think, all the binary blobs. But it does include a binary kernel for most of the Nexus devices, which is kind of strange. The source is available in a completely separate repository, but they have the actual kernel image itself as a binary in there. And they were saying that some of the Wi-Fi drivers in Android they get built into the kernel, and I guess that might be a reason why they have the binary there. But you can get those blobs from the binary-only drivers page, and they're really proud now that they've got them all up there, and they're trying to keep it up to date. Unfortunately, with OEM devices, things are much more closed, and the only way you can really get them is from stock ROMs or live devices, or sometimes OTA updates. It's usually easy to do that stuff, though. I mean, if you have your device, especially if you can root it, which I think that every device that's out right now has some public way to root it. So from those, you know, you can just pull them right off, whatever you're interested in. Just look around, you'll find some fun stuff, I'm sure. And for the stock ROM stuff, you just kind of use the device model. Search for the device model in stock ROM. You'll end up all over XDA developers forums and a handful of other random forums. And hopefully you can find the stock device for, or stock ROM for the device you're looking at. But the downside of that is that each OEM that makes Android phones, they kind of use their own proprietary packing format for these stock ROM images. So you might have to dig around a little bit to find some open source re-implementation or try to use the OEM's tool itself. So from a live device, there's a bunch of different places which you want to look to find this proprietary code stuff. A lot of it's on actual partitions, so there's a, you know, you don't think that a phone would have a lot of partitions, but actually, like modern, like the SGS4 or something, I think it probably has like 29 partitions or something on the device. And a lot of them, they don't even tell you they're there. You can't see them. They're not mounted. They're just kind of like some magical blob space on the, you know, flash that they do something with. Nobody knows what they do. It's not documented. So that's pretty fun place to play around. But you can dump all the partitions once you have root. It's real easy. Or you can even boot a custom recovery and do that. As far as on the file system, there's a few paths like /vendor and /firmware. And then a lot of times they'll have some stuff in /sbin or even just mixed in with the regular stuff in /system/lib or systembin. So the nice thing about from a live device, you know, especially you have the device there live, so if you're attacking it, then you can totally just, you know, attack it. You pull the files, you open them in IDA, you do some stuff, you're like, oh, I'm going to test a bug, you test a bug. That's really nice to have that all set up and there, and you don't have to worry about it not working on some other device yet, if you don't want to. But I don't know. So it works. It also works even when there's no OTA or factory images. Like if they had just released the Galaxy S4 yesterday or something, and you bought one, then you could totally just start pulling stuff off right away, and that's actually the only way you can really do much with it at the beginning there. I mean, it takes them a while to put out source code for the things that they do put source code out for. So, I mean, in that beginning life cycle of a new device, like there's a really big opportunity for doing binary stuff and pulling things directly off. But if you can get OTA and stuff, it's beneficial for a device you don't have, of course. So another thing you can do to find out what else is going on these devices, you know, non-Nexus devices, you can just kind of compare against a Nexus device. And here in the excerpt, I basically just show the version of these two devices that I was looking at. The top one is my Galaxy Nexus running the latest version, and then the next one is a Motorola Droid 4 that's running a little bit older version. And you can see that I grepped out the space to space, so that gets rid of all the kernel processes and just shows userland stuff. So then you can see that 56 things were running on the Galaxy Nexus, but there were 79 things. So there's an additional 23 processes running on this phone, even though it's not doing anything, just idling. And then at the bottom, I included this command line. It's nice because it kind of shows you what all the core services are that are always running, and you can just kind of grep those out, and that helps cut down on a little bit of noise, especially if you're actually trying to look at the output and see what's new. Also on the file system, of course, as you can imagine, you can look around once you have root especially, and then you can diff against the Nexus device again. It's just a few commands. You get BusyBox, and then you can run find. So this excerpt shows like me using the cluster actually. So I have a set of Ruby scripts that allow me to address all the devices at once and run like one-line commands that I expect to only have one line of output, or I can run things that are like more length of output, multiple lines, or I can just tell it, you know, hey Nexus 4, give me a shell, or hey Nexus 4, pull a file. It's a lot more convenient than working with ADB when it's just like the serial numbers, because serial numbers are not very identifying or human friendly. So I just wrote these little Ruby scripts to wrap that stuff. So the first part, I just pulled a version. I look for a couple of devices that are the closest possible version numbers of the Android version, which isn't necessarily indicative of anything. But then I ran just find on both of them, each of them, pulled the files, and you can see already that the Nexus S, when you look at the find output, is 4.2 megs, and the SGS3 has 9.3 megs. So like more than double. Just in find output alone. And these devices are both completely stock, like empty. They're not like, I don't put apps on them. I've never even connected to them into a network or anything. So, so then you can, then you can see I just grepped for the system lib to look at a subset of the file system to get an idea of what's going on there. And then looking at the lines of output, again, there's like, more than double of just libraries that are in system lib. If we go ahead and diff those, then you'll see the stuff in green is all things that are only on the Samsung Galaxy S3. They're not on the Nexus S. So these often are proprietary code, like libdrm wvm plugin. That's more than likely a proprietary codec for DRM. So there's tons of stuff like this that you'll find. Just the more you look, the more you find. So a final note, like make sure you do some analysis before you assume that it's closed source. There's a high likelihood you could just run the strings command and find some string and Google it and find some project that they started from and then they just build it, and they didn't have to distribute the source code because it's BSD licensed or something, and so then it's just bundled in there as a binary. You think it's closed, but the source is always something that'll help you a lot more if you're doing some auditing on stuff. So even though some stuff is closed, like I said, some stuff looks closed. It might be closed, and it might be like massively modified, but then it might have some structures that they never modified. So any little piece you can get when you're reversing a binary, and that's all you have, will help you. So that stuff's good to look for. So let's talk a little. So I apologize if you guys are well-seasoned reversers and everything, and I don't want to offend anybody, but I just wanted to gloss over some core concepts of reversing for people who may not be as well-versed in it. So the way I see reverse engineering, it's kind of like mainly two houses with static analysis and dynamic analysis, with static being anything you do that doesn't run it, and dynamic being pretty much anything you do that does run it. There was a lot of talk a long time ago, like which one's better? Oh my God, this one's better, that one's better. But I really think, and I know a lot of people might agree with me, that there's real power in combining these two houses of analysis together and using them to feed each other. So keep that in mind. Reversing ARM binaries, I think that the guys just before were talking about reversing some ARM with IDA. If you guys have ever tried that or not tried that, if you ever do try it, you'll notice that it's kind of a mess. And so I put these steps in here to give a hand with kind of what you have to do to actually use IDA on a modern phone. So I think in the last 2 years or so, pretty much every phone is ARM v7 compatible, but IDA's default ARM processor selection is like ARM v6 before any of the floating point, neon, vector instructions, and a whole bunch of other things. So if you follow these instructions, and I've got some shortcut keys for you too, this works a lot better and tends to produce a lot better results than the default. So string analysis, again, I said strings, run the strings binary, but if you look in IDA, everybody who reverses knows that strings are like your gold mine. This is where you find the stuff that makes it so easy for you to actually be oriented in the code without having to dig constantly. So Hexray's decompiler works pretty well. It helps to read stuff at a higher level, but it also helps you when you interact with it to recover structures and to do type propagation across interprocedural flows. So it really can help out a lot with that stuff and definitely speeds things up. I remember the first time I saw somebody show me using it, I was just amazed at how quickly they took some disgusting looking thing and made it look like something that a human might have actually written. But don't try to compile it. There are some issues with the Linux kernel handling in IDAPRO because in Linux kernel they're trying really hard to be very efficient, and so they write a lot of things in assembly, and then they break a lot of the calling conventions and do a lot of other weird stuff that they're not supposed to do, or shouldn't do maybe, but maybe it's faster, I don't know. But it throws IDA for a serious loop. Ilfac was really unhappy when I showed him some of the stuff that it was doing, but hopefully later when they release the next version it'll be better. So using symbols, of course, on Linux, on ARM Linux especially, a lot of times the binaries will have symbols. All the Nexus devices ship with user debug builds, which means they have symbols in all the libraries and all the binaries, but they're not full symbols, so if you want to have full symbols with source lines and everything, you have to build them from AOSP as well. OEM devices will also have symbols because exports are kind of a requirement as far as whenever there's a relationship between modules. They typically will always use the names, even though they could obfuscate them or something like that. They typically don't. They usually leave them in there, and that's a big giveaway. So it's common to find pretty good symbols and stuff. Unfortunately, and we'll get to it in a second, it's not all fun and games there. So differential analysis can really help in reversing as well. If you're comparing older versions of a binary to another, or like say, for example, you're looking at a particular service on an Android device on Nexus versus an OEM device, you can see then any of the changes that they've made to the original one, which could be very interesting since it's not open source, it might not be very good code. So comparing file system entries again, running processes, and also comparing specific files. The init script, which a lot of times you can't read without root, but if you read it with root, then you can check it out, and a lot of times that'll just show you right away like what new things, and even what privileges and where locations on the disk are, or on the flash, or on the memory, on storage, whatever you want to call it. I guess we can't call things disks anymore. But anyway, it'll show you that in the init scripts, and that's a great place to look. So yeah, I mean, usually differential analysis is just used for looking for known bugs, and I guess that could be used in Android, but nobody's really disclosing anything in Android, so you would really have no indication that you might want to go look for known bugs. So I guess they're also not fixing things, so maybe not. So, but it would be useful for watching the evolution. So if they're releasing a new version and during feature dev, and you're interested in auditing, then it may be very interesting to you for you to know that there's some new code to exercise or look at. So just some high-level tips with static analysis. Grooming your IDB helps a lot if there's a lot of errors or like indirect flows and stuff that you haven't resolved, and those are really painful. When you're reversing, of course, another tip I like to give people is to always look for functions with tons of cross-references first, because that's going to give you your biggest win, where you're going to be in this gigantic function, and you're just going to have a lot of calls to something, and everywhere in the code it's going to be the calls to this thing, and as soon as you go like look at it and understand it and give it a name that makes sense, then any giant function you go into, then all of a sudden it starts to make sense what it's doing just from that one call that you've identified. And also often those functions are usually logging functions, which are great to know where they are in code as well, as we go back to string analysis with that. So, so large functions are also interesting because they tend to be very complex and full of bugs. It turns out that humans aren't very good at keeping, 100,000 lines of code in one function and understanding that. What do I got here? Right. So if this is especially true if binaries don't have any imports, because then they don't have the nice symbols for you. You have to go then and look for small functions that are called often, and actually look at what they are, and then identify them and name them the common library functions. Unfortunately, IDAPRO does not do a great job with flirt style stuff for ARM binaries and things like that, especially with embedded code. So you kind of have to go find these things first, and then once you mark them up, then it makes everything easier when you keep going through. So on the dynamic analysis side, one of the easiest things to get into there is the logcat. If you have root access, then with logcat you can see all the logs, including the baseband logs and some other things. So you don't have to play with the switches on that to see the other stuff that doesn't show them by default. But it's there, and it's great also to see the strings that you see in the binary going through logcat, or being able to use that to confirm that you're triggering the code that you're actually wanting to trigger. GDB, on the other hand, although it's useful, it's not the most stable tool, and we'll get into some more reasons why it's not so stable. But on the plus side, it does have Python support in the latest GDB that's in the AOSP build. But it is, again, it is pretty slow to do remote debugging over USB, and over Wi-Fi is even worse. So as I said, symbols are a lot more important on ARM. With ARM Linux, like GDB depends on these special symbols, the $A, $D, and $T things, which indicate whether things are ARM code, thumb code, or data, respectively. And without these things being present for a binary, GDB basically has no idea if it should be in ARM or thumb mode whenever it goes into a breakpoint or sets a breakpoint or something crashes or whatever. So if you don't have those, which you won't by default on proprietary binaries that come from OEMs or some closed source stuff that might be rolled into Nexus devices. So since you won't have those, you'll have to deal with keeping track of thumb mode on your own, which is kind of a pain in the butt. But it does work, but not stable. So it will still crash on you. You'll set breakpoints, you'll tell it to go, it won't hit the breakpoint, you won't know what's going on, and you have to keep trying, and the GDB will crash on you, and you'll have to start over again. So good luck with that. Sometimes trying a different GDB binary works better. There's a lot of different ARM tool chains out there, so maybe one of the other ARM tool chains happens to be the one they use to build that particular binary. It might work a little bit better. In any case, for thumb mode, you can use the CPSR register to help you keep track of thumb mode as well at runtime. So debugging is slow, like I said. It's kind of a pain in the butt, and it's not that stable. So one thing that really helps is to do instrumentation or hooking. It's a lot more efficient. It does taint the address space, so for exploitation, it's a little bit questionable. If you're careful, maybe not such a big deal, but it does kind of taint the process a bit. But challenges with that are that ARM is a really sort of complicated, even though they use uniform instruction lengths, it's really sort of complicated architecture for developing your own disassembler. And in order to properly do hooking, they have, so they use PC relative addressing in ARM a lot because you can't load a 32-bit immediate all at once. So you either load 216 bits or you store the 32-bit value somewhere close to PC and then load it from there. And they will just have that straight up in the prologue, like instruction number 2 or something. And you'll be like, whoa, I can't really relocate that very easily. So especially not in a generic automated fashion. So you have to deal with all these things if you want to do the hooking stuff. Colin and I have been working together on the Android DBI a little bit. We're trying to work towards a release, but we're not quite there yet. Sorix mobile substrate supposedly works really well, and I've actually looked at some of the older code, but he's closed sourced it now, so the new code isn't available. But these both work, and I think there's another tool out there too called Expose Framework or something, but I think it may only do Dalvik stuff. So to go further on the dynamic analysis, the kernel and bootloader debugging is sort of possible with JTAG, but a lot of commercial devices that are out there, they have this disabled. They'll have the actual JTAG fuse blown, or especially with devices that have trust zone, which is almost all of them now, the bootloader that's very early in the first stage will just disable JTAG in software, in hardware by doing a control register very early in the boot. So and that stuff's usually verified and signed, signature checked and everything. So to get that stopped, maybe glitching, maybe something else. Maybe compromise the private key would work easily. I'm not sure. But so the USB UART cables also can be really helpful because you can get a console output from a device. And some guys told me that they saw some devices that actually were just giving root shells when they hooked up the USB UART cable, which was, I thought, very interesting. I hadn't seen that on any of the devices I tried it with, but it's certainly not unbelievable. If you recompile the kernel, the nice thing with the UART cable is you can start doing serial debugging remote with it. It's a little bit slow again, but it's definitely less efficient than doing instrumentation or hooking. But it's better than nothing. And if it's interactive and you're really just trying to hit a driver and figure out, am I hitting the function in the driver that's got this bug that I think is there, then it can be useful for that for sure. Outside of using an actual real-time debugger, like there's some files that are around in the file system that can help you do debugging too when you're doing dynamic analysis. And two of those are in the proc file system, is kmessage and last kmessage. So kmessage is kind of like the dmessage output, but you just cap this file and it just keeps scrolling it to you. Last kmessage is actually, if you crash the device, a lot of devices will create this from the crash buffer that it was storing. And when you reboot back up, then you'll be able to get like the full oops log and everything that happened in the Linux kernel. Changing the kernel command line also can be helpful because you can disable a lot of stuff like mitigations. Newer devices have some SE Linux, so you can disable the SE Linux or maybe some of the other custom kernel stuff that they had put in there. I have to go fast. So again, instrumentation hooking. One thing to note there, the Linux kernel has jprobes and kprobes, which are actually like software-based breakpoint things that are facilities in the kernel that let you do hooks. They're a little bit more efficient than doing breakpoints in userland or breakpoint with remote debugging because it's kind of all handled inside the kernel. So there'll still be like there'll still be an interrupt, and it'll have to handle it and stuff. But at least it won't have to like take the interrupt and say, "Hey, guy on the 115K serial port, you want to do something?" But still, again, the most efficient way would be custom hooking, where you're actually like injecting code and doing inline hooking and not having to deal with extra exceptions or interrupts or anything like that. So I'll just go through some auditing tips now. Auditing is a. Does anybody have a good way to describe it? Drawing a blank. It's a tireless process. How about that? I recommend taking breaks. So I'll just start with some methodologies. So auditing kind of falls into three sort of methodology groups. There's the top-down one, which is very methodical. You start by identifying places where you know that bad stuff or potentially bad stuff, or aka your stuff, comes into the program. And then you just kind of follow that through the program until you see something horribly wrong, which usually isn't very far. But then you can also do API-based stuff, which is pretty useful. It can be frustrating though, because you may find a string copy call looks totally like you control it, and then some butthole put a string length check like in some function right in the middle of this gigantic call stack, and it takes you 2 days to find it. But sometimes it doesn't happen like that. Sometimes you find it right away. It's great. But format string vulnerability is another one. That's a particularly hard one to find in binaries because of the way that they're implemented by the compilers. But if you can find that stuff, it's really fun. Of course, the other API stuff, checking memory allocations, is a great way to find bugs as well. Checking static buffer usage is a great way too. You can just look around for functions with big stacks, big stack frames, and then go see what the hell they're doing with so much stack frame. Usually find bugs that way, lots of loops, buffer overflows. And grepping also works great too. So like a lot of times, I mean, I don't know if I could count the times that I had grep for like malloc with a parenthesis with a asterisk inside of the parentheses and then a closed parenthesis, and found just ridiculous bugs. I think it will still find you bugs. So anyway, sign extension bugs are much harder to find. Usually they look like a cast to assigned integer, or sometimes they just look like two usage assigned integers that really have no business being assigned integers. And sometimes they're characters that get assigned to integers or even longer values. It can be really subtle and hard to see in source code and in binary, but in binary code it can be a little bit more obvious. So just some quick tips. Learn as much as you can about whatever you're attacking. If you're attacking a DLNA server, you should probably know what the hell DLNA is. You should probably know how most people implement it. You should probably know you know, as much as you can find out, and especially the underlying operating system APIs and architecture will help you immensely when you start doing dynamic analysis, especially and especially for auditing, because there are a lot of subtle quirks that vary between different operating systems and architectures. So some entire vulnerability classes may or may not be exploitable on one architecture versus another. So it's important to know all those things. Again, take advantage of everything you can get your hands on. If you can find some docs, then read them. If you can find some source, then reference it, read it, whatever. But still, don't make any assumptions, because that's really what sort of like auditing is you're looking to find where somebody made an assumption, and you call them out on it. Really, you're like, yep, that's not, you know, that's not a law right there. That's not you can't prove that. So I can actually prove the opposite. So don't make any assumptions. Try to recheck and double check and make sure that what you think is correct is absolutely correct. Take lots of notes and make lots of comments. I can't tell you how many times I like audited for 6 or 7 hours and then didn't take any notes or anything, and the next day I had no idea what I'd done. I mean, when you're 8 hours in staring at IDA, like, yeah, you're pretty much a vegetable at that point. So, yeah, take lots of notes and comments, take breaks, take a breather, let your subconscious absorb some stuff. So binaries versus source. Binaries are actually a lot better in some ways, but of course they're not better in all ways. The nice thing about auditing binaries is the macros in C and C++ get eliminated, so you don't have to deal with grepping and using C tags and following like 85 nested macros to figure out that it's just doing an assignment or something like that. The other thing is compilers can do really horrible things, including like just emit absolutely wrong code. So you may see that and you may be completely confused, and you may wonder what kind of dumbass programmer wrote this code, but it isn't their fault. Not always. Also, comments can be really misleading if you do source code auditing. If any of you guys have done that before, you'll be looking at some bull straight in the face, and you'll be like, what's going on here? And then the comment will be like, oh, this is safe. And you'll be like, oh, that's safe, okay. So not having those right in your face, it does help a lot. It helps you not make assumptions, right? Because if you read somebody's comment and they made an assumption, and you're going to make the assumption they made, and then that's not going to find bugs. So the other thing is it's really kind of a pain in the ass. Like I said, 8 hours in IDA, you're a vegetable. So people tend to not want to sit in front of IDA for 8 hours. And if you don't sit in front of IDA for 8 hours, you're probably not going to, find all the bugs. Not that you'll find all the bugs, but anyway. So people don't want to do it. It's like it's intimidating, right? You tend to do things that you enjoy, and vegging out in front of IDA for 8 hours may or may not be that. There might be more fun things to do, like look at cats on the internet, or I don't know. Maybe you can just crash your Android devices over and over again and watch that. That's fun. But cons, of course, it's harder to see stuff on the higher level when you're looking at it down in the weeds in the assembly. The hex raised decompiler helps with that, but it still can be kind of hard to see the great big picture that you would get from like an architecture document or something. Binary auditing definitely requires assembly skills. Even with hex raised decompiler, you're totally going to be like looking at the decompiler going, that doesn't make any damn sense. And then you're going to look at the assembly and you're going to be like, I don't know why decompiler doesn't work, but it's obvious what's going on. So it's still going to require assembly, especially for doing ARM stuff. So again, it's slow going, and dealing with indirection is a real pain in the butt. So let's go into a little bit of the attack surface, kind of on these different levels where the proprietary stuff is found. The first one is bootloaders. So in the bootloaders, like they basically just start dealing with partition data and all kinds of other stuff. They have to. They don't really have any choice. They're really dumb. And when you look at the code for one of these things, it's basically like just a driver for the flash and some crypto, and that's it. Maybe they have some checks to see if you're holding down a button so they can give you a different menu or something like that. Draw a splash screen. That's all they are, really. So they don't have much to deal with other than just raw flash and partitions. There's no kernel or anything going on there. Let's see what I got next here. So I had a case study actually in the Samsung Galaxy S4 bootloader. Dan Rosenberg found this bug where it allowed you to bypass the secure boot chain. So the devices for AT&T and Verizon have what's called a locked bootloader, which means that you're not allowed to flash your own kernels or system images or anything like that. So they do actually like full RSA verification on each stage in the bootloader. So every stage verifies the next stage, verifies the next stage, all the way up until the actual Linux kernel boots. So he found that Samsung's A-boot was kind of based on the open source LK bootloader. So he was doing what is a superforce multiplier, where you're looking at the binary and you're seeing everything very concretely in the assembly, but yet you have the source code and the strings are matching, and you're like, okay, yes, all right, it's the same, it's not the same, it's not the same. So you can go fast with that, and it's great. So he found actually some changes that they were in there, and he went ahead and found this bug here. So the excerpt here shows kind of his pseudocode based on the changes that they had made to the open source version. And does anybody see the bug in this? Who's familiar with this bug? Is anybody familiar with the bug? Got one person. 2? 3? Okay. You guys are shy, huh? So this bug, basically the boot image is something that Android uses. It's just the kernel and the RAM disk kind of smashed together with a little header on it. And this is the last thing that happens after a secure boot chain. So the last stage bootloader in this case on this device actually read the header from this boot.img, which is completely controlled by whoever can write to the flash. So it was doing this. It took, in this header, HDR is a structure that basically just pointed directly to the beginning of that on the flash, right? It was read directly in, and it wasn't tested or checked or validated or anything like that. And so what they actually did here is, you can see where they have an MMC read here where it says load the kernel. They actually used the address to load it into directly from the header. So if you put any address in memory in the header and point it there, it'll go ahead and read whatever's at that offset in the flash to that address. So what he did was he took the boot.img and he pointed it into the A-boot's code itself. So the A-boot basically went to go read the kernel to verify it and actually overrode its own code with code that he put in there that was the kernel. And then in his code, he just simply fixed up the mess that he had made and then returned that, yeah, the verification was okay. So that let him do the whole, custom kernel thing with the locked bootloader. That's the last stage bootloader, so we could see possibly a fix for that, but if it was any earlier, I don't think we would see one probably ever. So Trust Zone. Interesting thing about Trust Zone is Trust Zone is only accessible from ring 0, so you have to be in the kernel in order to even send any commands or get anything back from Trust Zone. Like I said earlier, they had a userland driver. They got a whole crazy stack going on, but ultimately there's got to be something in the kernel that's talking to it. It also gets talked to by the bootloader, of course, but things are a little bit more open in as far as security when you're that early, because none of the untrusted stuff has really been executed yet. So another bug that Dan had found, he found a bug in the Motorola version of the Trust Zone OS kernel. It was a really awesome bug. I had seen similar bugs at some point, but this one was really neat. So what they do is in the Trust Zone they use what's called Q fuses, and this is part of their internal RAM. It's just really small. These things, once you set them, you can never set them back. They're like they're atomic fuses for all intents and purposes. So the OEM unlock mechanism used these, and basically what they allowed you to do was they would set one to say that it's locked, and then they would have another one that they could set to say that it's unlocked, or yeah, I think that was it. So Trust Zone uses this instruction called SMC, and it's basically just like a syscall from userland to the kernel, but it's from the kernel to Trust Zone. So it's basically the same thing as the syscall. Abstraction is almost exactly the same. But the code happens, obviously, it's processed inside Trust Zone. So Dan found a bug in it. Here's the pseudocode for this one. As you can see, the code is controlled by the person who's doing the SMC, and this argument 1 is also the first argument to the SMC. So, and then finally the arg2 is also controlled by the attacker. So at this point, they're just writing stuff wherever the hell we want them to write it. So that's really not good. So he used that actually, and this is probably the most trivial use of this bug. I mean, it could be, I imagine, much nastier than what it was, but he used it to override a flag that indicated in trust zone OS kernel that it was outside of the bootloader and that it already had booted, which disables a lot of functionality, including the OEM supported unlock code. So he set that back to 0 and then just started calling the stuff that you're not supposed to call unless you're in the bootloader. So voila, he had the unlocked bootloader. All he had to do was use IDAPRO. So lower level stuff like baseband, I haven't gotten into it. I'd like to get into it. It's a very interesting area, but it's definitely a lot of proprietary mess, including completely proprietary architectures and things like that. But they have 2 attack surfaces mainly. They have kind of one from the radio and one from the application processor. We've seen some talk and stuff about RF attacks before, but not that much. It's much more common to see these attacks from the application side of the processor. And those attacks, like some of them that give you S off, which stands for like security off, and basically on some HTC, and a lot of HTC devices, maybe even all of them, what they do is they lock the NAND so that you can't write to the flash at all unless you turn this flag off. And usually you can't turn the flag off without much lower level access like the bootloader or trust zone or from the baseband sometimes. And so we've seen a number of SOF tools that basically talk with @ commands and exploit vulnerabilities in the baseband from the application side just to get in there and turn off this little flag so they can write to the system partition again. Of course, there's also the hardware attack surfaces of any sort of device that you have. The USB UART on the Nexus 4, you can actually do that with a headphone jack. We put up a blog about that, I think, a few weeks ago. And then there's a special OTG cable that you can build that just puts a resistor between ground and one of the pins, and that'll let you do UART on Samsung devices. I think there are other cables out there to do it for other devices, but those are kind of like the 2 that I've looked into deeply and actually have used to do KGDB and a bunch of other things. Again, JTAG's usually disabled, but that doesn't mean it will always be disabled. It's worth a shot if you can find it. For devices that have unlocked bootloaders, you might be able to hack up some firmware that's in the bootloaders where it's actually going to disable the JTAG, and you can just make it stop disabling the JTAG, which is convenient. Although, if there's signature checking, you're not going to be able to do that. And then, of course, other bus-based attacks if you're willing to take your device apart and start poking at it. The kernel attack surface is largely analogous to just regular Linux kernel. Obviously, there's some complications with it being ARM. There's also additional code and additional attack surface because of it being Android. There's a lot of things that they had developed for Android specifically to support things like multiple modes on the USB port and other things like that. But in general, like the software that's there, especially the proprietary stuff, it tends to just have a traditional attack surface. Especially if they're kernel drivers, they're just going to export maybe some proc or sys or debugfs stuff, or they'll just have some custom implementations of the POSIX API functions, like they call them file system operations or FOPs or whatever in the Linux kernel. You'll see them everywhere. But it does depend largely on the type of the driver. I doubt that there's going to be a lot of third-party modifications, including even OEMs or anyone else, that's going to involve like new syscalls or anything, but it's totally a possibility. And then in user space, there's a lot of attack surface as well, although it's mostly local for privilege escalation. Of course, file system permissions. We've seen a lot of attacks on Android that have unsafe shell operations, doing chmods, chowns, like just deleting files and all this while like having a directory right in the middle that was completely like writable by everyone, which is typically not a good idea. The socket endpoints are also a really interesting attack surface. Any app or any program or whatever that you have on there can start listening on just anything. With the exclusion of TCP and UDP, you can't do without INET privileges. But the rest of these, Netlink, Unix, abstract domain, which is new for Android specifically, those you don't need any privileges for. And in particular, abstract domain sockets are very interesting because you cannot secure them. There's no credentials associated with them. They're completely open. Of course, content providers and broadcast receivers are attack surfaces, even for proprietary code. If there's a service that's new, they've got a small Dalvik stub, and it just calls into like some massive library, then you're going to want to be able to tickle that, and that's one way you can. So you can also enumerate some of the proc file systems. You can use the proc file system to enumerate some of the other attack surfaces further, including like listing sockets that processes are listening on or have open or connected to. You can look at the permissions of processes, including like what their users and supplementary groups are, and those can all really help you to determine kind of what you should go after, and also like what could be dangerous there. So I had one more case study that I had found. So I looked at this tablet again. I had mentioned I looked at this tablet because they have a supported OEM unlock method where you can totally go to a website and say, oh yeah, I want to unlock. That means I don't want my warranty anymore. I'm going to go ahead and do that. And I didn't want to do that. I want to keep my warranty. So I keep my warranty. Well, it's actually refurbished, so I really need to keep that warranty a little bit extra. But anyway, so I wanted to keep the warranty. So I decided to look around for some proprietary stuff, thinking it'd be easy. So I found a driver that actually implements the exFAT file system, and I don't know who's familiar with that, but this is a file system by Microsoft that was made and licensed basically to everybody. So it's one of those things where when people say that every Android device Microsoft gets a cut, well, that's part of why. One reason. There's a couple others, but that's one reason. So this file system actually is purported to be the most widely interoperable. So I know a lot of people have Macs, and you can mount NTFS and you can read, but you can't write. And then VFAT's kind of flaky. But supposedly exFAT works on that. It works on this tablet. It works on Windows, sort of. So anyway, I opened up the driver. It was pretty quick, and within 1 hour, I had stopped fighting IDA, finished emailing ILFAC, and then started looking at code. And then let's see if it has an IOCTL handler. So I look for one. Here, let's look at this one from a core file system driver that's just pulled out of Linux kernel. This is actually a subfunction that's called from the IOCTL handler. This prototype that's on the IOCTL handler in the comment at the top is a typical prototype for an IOCTL handler function in Linux kernel. The file P is just a structure dealing with the file descriptor that you have open. The CMD then is the IOCTL code that you would pass, and then arg is just the pointer that you would be passing in from user land to deal with stuff. So what they do here is they use that and they pass it to the user attribute thing of the subfunction, and then the user attribute function then just writes some stuff there that it had gotten from these attributes, right? And it looks good, there's nothing wrong with that. But then when I looked at the binary for this one, and I actually used the Hexrace decompiler to get some pseudocode, this is kind of what their code looked like. Does anybody know what's wrong with this one? Okay. So the difference is you can see there's a put user here, but on this one you have underscore put user. So what's interesting is in Linux kernel, the underscore xxx function, this is a comment straight from Linux kernel right next to where this put user thing is in a file. It says these don't verify the address space. So that means any code that looks like this, if you put a kernel address in for arg, it'll go ahead and write that. No check. So since they don't check, then we can go ahead and write, just whatever. You can write to the middle of a function that's in kernel mode. They don't prevent you from writing to code segments or anything else. So after I figured out something fun to overwrite, then it took about 6 hours to get it working. I think 3 hours of that was me trying to figure out how to format this SD card with exFAT file system. It turns out if you want to try that at home, don't try to use your MacBook SD card slot, because apparently that doesn't do it. But I switched over to a like Best Buy like USB external SD card reader writer, just like that. Most disappointing 3 hours of my life. And I actually had that same problem before, not exactly, but like problems with SD cards, and then that thing worked again in that case. So let me try to do the demo real quick. I apologize if it doesn't work. It was crashing on me in the next room. It was really kind of unfun. And it's not in movie mode, so it should be like really uneventfully. Okay, it worked. Yeah. So that's all I got for the demo. I actually wanted to show you guys. Want to see some of the cluster as well? Like I was playing around in the Broadcom talk earlier. I lost the whole window. That wasn't cool. There it is. So there I ran earlier a command that dumps the Linux kernel version from all the phones that are connected. So you can do that, or I think I had another one earlier. They are looking for the Broadcom firmware for all of them. Some of them like don't have anything. Some don't have anything, but there's different versions. If you guys need any of those, let me know. So yeah, it's fun to have a lot of Android devices and play with them. A lot of times you'll be surprised by what you think might be on a lot of devices, and it turns out it's on like one device, and vice versa. Sometimes you'll think that, like with the Broadcom thing, you'll think, oh, well, maybe that's just a couple of devices, but oh no, it's like 50% of them or something like that. It's interesting to be able to query stuff like that, and if anybody has any queries, you're welcome to hit me up directly, privately, email, whatever, however you want to do it. I'm welcome to run. I'm more than happy to run the commands for you and send you back the output under personal NDA or however you guys want to do that. But let's get into some conclusions. I only have a few conclusions here. Basically, again, the devices are all snowflakes. So if you dig down into some code that's probably only on one device or one device family, it's probably more likely to find bugs and probably a lot less likely for them to fix the bug. Then the ARM architecture, of course, is the giant pain in the ass with the instruction set being so complicated, and the different processor modes being such a pain to deal with, especially without symbols. But again, the proprietary stuff is definitely worth looking at. There's plenty of code to look at. There's no way I could have hoped to look at every piece of that code. I mean, like the Trust Zone firmware itself is like 512K of just like core OS stuff that's really disgusting to look at. Like a part of it's calling into like physical addresses and stuff, and that's really hard to follow that stuff. Anyway, definitely buggy code. So if you want to look at that stuff, I love to hear about people crashing stuff or whatever. And if you have any unwanted Android devices, there's still a little space on that table. Of course, after you see the table, you probably don't want to get rid of your Android devices. You probably want to get a bigger table. But anyway, the hub in that one, by the way, is called a Mondo hub, 28 port hub. It's 4 of the ports are USB 3. It's a nice hub, although it's a little bit flaky sometimes. Does anybody have any questions? Yes? What was? Well, I hope not. God, I hope not. Nobody wants that. So the question he asked was, what about trust zone? Do I see it as a place to hide malware? And you said something about, did you say PSP? Well, so ARM actually supports virtualization separately. That's different than Trust Zone. Trust Zone, I think, actually, I'm trying to remember where it is in the stack. I think Trust Zone is more privileged than the hypervisor. It's supposed to be like super low level, really, to do highly sensitive crypto operations and things like that. As far as a place to hide malware, if the malware is really small, yeah, you could do that. But it's going to have to be really small, or you're going to have to utilize that encrypted file system that comes out into the userland area. It's definitely not impossible. As far as what we'll see it's used for, I think right now it's primarily used for like DRM and a few other, signature checking in bootloaders and a few other things like that, where they are really trying to keep things under wraps. As far as whether or not I think Trust Zone is like the silver bullet to security, no, I don't think so at all. I think it's just a different attack surface with, more buggy code behind it, maybe even more buggier code than other code because they think it's so secure. But yeah, any other questions? Come on. How about, okay, go ahead.
Have you seen any interesting attack surface from the basement perspective? You mentioned the radio interface layer. Anything else?
Okay, so the question was, have I seen anything with relation to the baseband that's attack surface? He had mentioned that I had said RL again. So not really. I mean, not more than what I had said already. It's kind of weird because the API, the way that RL works, it's kind of like it just has like two methods or something. It's like process response and send request or something, and that's all it does. Everything else is completely proprietary. It all runs in the same process. So RLD, I think, it usually runs as the radio user, and it usually has access to stuff that no other process has access to. I mean, in particular, the baseband. So if you compromise that process, you're already in a really advantageous place where you can start SMSing and you can man in the middle people's communications and replace them with whatever you want. If you want, some guy to get a text from his boss that says, let's go to lunch, but it doesn't say let's go to lunch. It says you're fired. You can do that. But like as far as additional attack surface, a lot of the more granular attack surfaces will require deep reverse engineering in the vendor RL. And it's very specific to sort of like the protocols that are supported by the carrier, whatever that supports that phone. Yeah, it's tough. Like there is a tight knit between the communication between the RL and the baseband, but I mean, you can watch it and do protocol reversing as well. So. You kicking me out? Okay. Thanks. If you guys have more questions, just hit me up either online or out in the hall or wherever. Thank you.